Part 4 of lesson 26, the formulas. So here is where we're going to do a mathematical application of what we've learned in the previous part of lesson 26. And first of all, we have the mirror equation. Oopsie, the mirror equation. This is the mirror equation. It's on your formula sheet. We have 1 over f. F stands for the focal length. And the focal length can be positive or it can be negative. It's positive if the mirror is converging, and it's negative if the mirror is diverging. We have DO, which is the distance from the mirror of the object, and DI is the distance of the image. And these ultra special notes for using mirror equations really are ultra special. Unfortunately, it means you kind of have to memorize them. So you have to memorize that the focal length for mirrors is positive if it's a concave mirror. The general rule, focal length, is if it's converging, it's positive. If it's diverging, it's negative. And so for concave mirrors, you can have a positive focal length. For convex mirrors, you can have a negative focal length. Distance is positive if it's in front of the mirror, negative is behind the mirror. Erect images, ones that are upright, have a positive height, and inverted have a negative height. So let's go through example number 2. Example number 2 says a convex mirror has a radius of 20 centimeters. An object is placed 30 centimeters in front of the mirror. Determine where the image will appear. Now, I strongly advise you to do a little sketch at least. If you get some graph paper and a ruler, you could actually figure out the answer just graphically, but we're going to do algebraically with a sketch, because the sketch will at least give you an indication of whether you're in the ballpark. So here's my little sketch. Principal axis, it's a convex mirror. Convex. So, oopsie. I want to put my object on the left side here, so I'm going to draw it this way. Convex. It has a radius of 20 centimeters. So since it's convex, I'm going to say that I'm going to say that this is the center, the radius of 20 centimeters. And here's my focus right here, which is going to be 10 centimeters. So if it tells me the radius is 20 centimeters, then my focal length is 10 centimeters, and it's also negative because it's behind the mirror. Okay. The image, it says an object is placed 30 centimeters in front of the mirror. So let's say so 30 centimeters is actually going to be way over here. Doesn't matter what size you draw it. And now I'm going to follow my rule so I can at least get an idea, a ballpark of what the answer is going to be. Rule number 1, parallel, and therefore it's going to reflect through the focus. Oops, I forgot to put that there. Through the focus, it doesn't really matter if you draw a dotted line or not. We know it's going to go that way there, but it's going to be go through the focus. And then my second rule, center. So if I draw a straight line from the object to the center, and there we go, more or less. And my answer is right there. So that, and you can see that it's smaller, it's upright or erect, and it's virtual. And this is 10 centimeters here. Where is it? Well, it's somewhere in between 10, closer to 10 than 5. So at least that gives me a ballpark answer. Now let's do it algebraically, which is always going to be the preference. If we can do something algebraically, 1 over f equals 1 over dO plus 1 over di. We've already determined the focal length is 10 centimeters, and it's negative because it's a diverging mirror. So you have to put the negative in there. And we can also say that the original distance is 30 centimeters. And we're trying to calculate di, the distance of the images, and we have deduced that it's somewhere between 0 and 10, closer to 10. Let's rearrange this formula for di. Di equals 1 over f minus 1 over dO. Right, just take this move it to the other side by subtracting it because they're separated by addition now. Plug in the numbers. 1 over di equals 1 over negative 10 minus 1 over 30. Now don't do that naughty mathematical thing that some people think is acceptable here and just invert everything. Don't just go, oh, okay, therefore di equals negative 10 minus 30, because clearly that's not right. That is so mathematically wrong, I can't even talk about it without having a panic attack. So I'm going to erase that. There we go. And we're going to add these like fractions. Hey, remember all those times in elementary where you said, well, junior high, we said, well, never use fractions. Oh, well, here they are again. We're adding fractions for the rest of your life. You will add fractions, and you will love it. 1, I'm going to change this to negative 30, and therefore I'm going to change this to 3. Because 3 over negative 30 is the same as 1 over negative 10 minus 1 over 30. 1 over, oops. 1 over di therefore equals, so remember this negative here, really can, I just put it there, so that'll be negative 4 over 30. Okay, and at this point you can cross multiply. Negative 4 di equals 30, and therefore di equals 30 divided by negative 4, which is negative 7.5 centimeters. Wow, not bad at all. Look at the original, the sketch that we did. Does that look like about 7.5 centimeters from there to there? Sure does. 7.5 centimeters. So even a rough sketch will give you a good answer. Said if you do this with a ruler and graph paper, you could get the exact answer just by doing it carefully on a graph. Okay, so that is part 1 of the lesson. The second part of the lesson is the magnification equation. Is the magnification equation given to you on your formula sheet. This is one of those formulas which has 2 equal signs, which just means you can use any combination of 2 of the variables. So in other words, you could say m equals hi over ho. M is magnification, hi height of the image, ho height of the original. Or you could say that m equals negative di over do. Or you could say that negative di over do equals hi over ho. So you're just going to use a combination of 2. Okay, and the magnification, you've also got some ultra special notes for the magnification equation. It's the same kind of concept. If for the heights, they're positive if they're above the principal axis. In other words, if they're erect. And if they're inverted or upside down, then they're negative. The magnification sign, if it's positive, positive magnifications are above the principal axis and negative magnifications are below. For the magnification size, if it's greater than 1, then you're going to get an object that's bigger, and if it's less than 1, you're going to get an object that's smaller. So for example number 3, it says, for the same situation from example number 2, determine how tall the image is if the object is 5 centimeters tall. So in other words, if the height of the object is 5 centimeters, what is the height of the original? And very quickly, let's go back to our solution, and we can clearly see that it is quite a bit smaller than the original. Here's the original. Here's the image. This one's quite a bit smaller. So we expect an answer that's less than half. Let's do it algebraically. The height, that's what we're trying to find, the height of the image. We know that the original distance was 30 centimeters, and we calculated that the distance of the image was negative 7.5 centimeters because it was behind the mirror. Given those 4 variables, which variation of the permutation of the formula are we going to use? We're going to use this one. Negative di over do equals hi over ho. we're solving for HI, so we want to rearrange the formula. You don't have to, but if you want to, it's just going to be negative DI times HO divided by DO. Right? Cross multiply and then divide, which equals negative. Now, before we do that, let's just go back to our diagram there and ask ourselves a question. Ask ourselves, is the answer going to be positive or negative? And since it's upright, we know we should get a positive answer. So let's see if that bears out. Oh. Here we go. So it's going to be negative. There we go. We already know we're going to get a positive answer because the negatives just canceled out. 7.5 times HO, which is, I can't see, 5 divided by 30. And if you stick that into your calculator, you end up getting an answer of 1.25 centimeters, which seems pretty reasonable compared to our diagram. We knew it was going to be smaller. So the original was 5 centimeters. The image is 1.25 centimeters. And then the B part of that question, or the second part of that question, let's call it B, says, also determine the magnification. And since we've determined HI, we can use any permutation of the formula. Let's just use the easiest one, the one that we probably think is the correct one. We'll use this one. Negative DI over DO, which equals negative 7.5 divided by also, let's ask ourselves, magnification. Is it going to be less than 1 or greater than 1? Well, the image is much smaller, so it's going to be in between 0 and 1. And that would just be negative 7.5 divided by 30. And that turns out to be 0.25. No units, because the centimeters will cancel each other out. Which means it's essentially 1/4 the size of the original. Which again really makes sense, because if this is 1.25 and we multiply that by 5, what do we get? The original, 5 centimeters. So though that's the magnification equation, and then you've got the mirror equation to deal with, and gives you a way to solve all these problems algebraically, even though solving them graphically is just as fun. See you next time.